All right, looking back, we've been looking at making these enolate anions, and the last thing we did was put halogens, alpha to the carbonyl carbon. Question, okay, so you put a halogen alpha to the carbonyl carbon of your ketone. What can we do with that? Well, very simply, we've got a halogen on here. We can do substitutions or eliminations. If you take cyclohexanone, Br2 under acidic conditions, nope, under acidic conditions, we're only adding one bromine. So that's a more synthetically viable option. We add the one bromine alpha to the carbonyl. If we add lithium carbonate with lithium bromide and DMF, we can do an elimination reaction, and we get an alpha beta unsaturated carbonyl compound. Hey, we've been doing some fun stuff with that. Say, react it with a Grignard reagent. Where will it add the R group? Where do Grignards add R groups to alpha beta unsaturated carbonyl compounds? That's right, 1, 2, they added to the carbonyl compound. What if we added organocuprate to this molecule? That's right, the R group would go 1, 4. Hope you remembered that. If you didn't, no problem. You have a final exam coming up that will test you if you have or not. And who knows, maybe I'll throw it on the next exam too, just because I'm feeling mean. Also, take this halogen alpha to the carbonyl here. If it's a decent leave-in group, you add a base, a nitrogenous base, and amine here. You can do a little SN2 reaction and put the amine alpha. So those are examples of two reactions you can do once you have halogenated the alpha carbon. Let's look at enolates alkylation though. Or excuse me, this is after you've halogenated the alpha carbon. Let's look at what happens if you want to alkylate. Let's make a carbon-carbon bond, creating a bond between two carbons and specifying which carbons. Not the easiest thing to do all the time. So our main way of doing this, we're going to just deprotonate the alpha carbon's hydrogen to make that enolate anion, that carbanion, and then we need that carbanion to act as a nucleophile and attack an alkyl halide in an SN2 fashion. So in general, you're going to be looking at a primary or secondary alkyl halide. So here's the general gist of it. We take our carbonyl that has a hydrogen alpha to the carbonyl. LDA-THF minus 78 degrees, we know is going to snag off that hydrogen. If it was unsymmetrical, it would snag off the less sterically hindered hydrogen, the hydrogen on the less substituted carbon, to make that enolate anion. And that enolate anion will attack the R group of an RCl or RBr and put that R group on that alpha carbon. So we're extending the length of the molecule, adding more carbons to it. So let's just go through some examples. Take cyclohexanone, LDA-THF minus 78 degrees, puts a negative carbanion right here. That negative carbanion will attack the carbon that contains the iodide in this alkyl halide. The iodide will leave, and we put on this ethyl group right on that alpha carbon. And note the geometry of the carbanion is trigonal planar. Therefore, this ethyl group can come in from the top side or the back side. Well, technically, our enolate will attack this carbon from one side or the other, and we will get the racemic mixture of the two enantiomers. We didn't start with a chiral carbon, we ended with a chiral carbon. Not optically active. Our products cannot be optically active. We need the racemic mixture. All right. Let's look at this ester right here. If you take this ester, note this is an oxygen here, so these three hydrogens are not in play. They don't do any of the chemistry we're talking about. Only alpha to the carbonyl is going to work, and so we've got these three here. LDA-THF minus 78 takes off one of these hydrogens to make the carbanion. Carbanion attacks this carbon here, kicks off the bromine, and this ethyl group ends up being on the other side of that CH3. It's a CH2. Comes CH2 with the ethyl. Note, we've taken this one alpha carbon, a methyl alpha to the carbonyl and have now made a propyl alpha to the carbonyl by doing this. And if we had a longer chain alkyl halide, we would get a longer chain on that side of the carbonyl. Note we noted that we have carbons alpha to the carbon of a nitrile that also make enolates. LDATHF minus 78 puts a negative carbanion right here. That becomes a CH negative, and it can attack this methyl group, kicking off the bromine, and put a CH3 there. Yes, that's now a chiral carbon, so you have to worry about its enantiomer also. All right. Now, what if you have an unsymmetrical ketone? Recall that if we have this cyclohexanone here, 2 ethyls on this carbon down here and a methyl up here, LDATHF minus 78 gives us the kinetic product. It takes the hydrogen off the less sterically hindered carbon. It's going to take one of these hydrogens, making this carbanion. That carbanion can then attack this methyl group of the methyl iodide to put our methyl group on the other side of this methyl group. Note this is the kinetic product. But what if you wanted to put the methyl group here? What if you said, okay, I see that. LDATHF minus 78 is going to put the methyl group on the other alpha carbon because it's less sterically hindered. I want to put my methyl group on this alpha carbon right here, the more sterically hindered one. There's a hydrogen there I can snag. Well, that'll be the thermodynamic product. So we do thermodynamic conditions, sodium ethoxide and ethanol at 25 degrees, puts our negative charge here, and that will attack this carbon, and we'll put it right there. Alright, this video is going to be a little bit short because we're going to look at a couple of syntheses coming on that are just really useful and real cool, and I don't want the video to get too long when we're looking at this cool stuff.